Section 6.2 Differential Equations, Growth and Decay. In this section, we'll see how to use separation of variables to solve a simple differential equation. Separation of variables is an important term. Use exponential functions to model growth and decay in applied problems. This is going to remind you of pre-calculus. So, let's start with an example. We want to solve the following differential equation. So we want to find the function y which satisfies this equation. So the derivative of y would be equal to 2x over the original function. If y prime equals 2x over y, I can rewrite this as dy dx equals 2x over y. I didn't do anything here. Y prime is always the same as dy dx. The next step is the important one. This is what we call separation of variables. What I do is kind of like a cross multiplication, and what I'm trying to get is to have on one side of the equation all the terms with y, with dy. On the other side of the equality, I want to have all the terms in x with dx. So here I've separated the variables. Y dy equals 2x dx. And this opens the door to integrating. I can put the integral sign here and look at each of these two sides of the equality separately. So the integral of y dy is 1/2 y squared plus a constant, I'll mention that. And this side of the equality, the integral of 2x dx, is x squared plus a constant. So this is the answer, but we'll just put it in parentheses for a minute to explain why only one c is needed. Why didn't I write here 1/2 y squared plus c2, for example? So here is the explanation. If I had done that, the integral of y dy really is 1/2 y squared plus a constant 1. The integral of 2x dx is x squared plus a second constant that I call c2. What I can do if I write that is subtract c1 from both sides, and then if this is a constant and that is a constant, I can just give a new name to that constant c2 minus c1, and I fall back to what I had written earlier. So when you're integrating on both sides, you only need to put plus c on one side. We're not quite done here. This would be an implicit form. Sometimes it's enough, sometimes that's all you need to do. 1/2 y squared equals x squared plus c. Sometimes you need to find the explicit expression for y. Explicit expression means you want to write y equals and everything on the other side. So let's move on. From here, I'm going to multiply by 2. Y squared equals 2x squared plus 2c. But instead of writing 2c, since it's still a constant, I'm just going to give it a new name. And therefore, y squared equals 2x squared plus k. K equals 2c. So in the end, y is equal to plus or minus the square root of 2x squared plus k. There are many functions that satisfy this differential equations. Actually, there's an infinity. You can pick any k you want, and you can decide whether you want a plus or a minus. Any of these functions would satisfy this equation. If you want to try, go ahead. Exponential change. If a quantity y increases or decreases at a rate proportional to the value of y, we can write the following differential equation and solve. So first, what does it mean, a rate proportional? If a quantity A is proportional to B, we can always write it like that. A is proportional to B. For example, A equals 5B. In this case, the rate of this quantity is proportional to the quantity itself. The rate of y is proportional to y. That's awesome. It's a differential equation, and I can use separation of variables to solve it. So, separation of variables, I'm going to multiply by dt, so dt appears on the right, and I'm dividing by y, so I have 1 over y dy equals k times dt. You notice that there is no t in this equation, so we have nothing to put with dt. We just keep the constant k with dt. We could also divide by k, it doesn't matter, it would bring it to the other side. It doesn't matter, but we're just keeping it here in this example. Actually, it's much nicer to have k rather than 1 over k here, so let's keep it here. Alright, we can integrate both sides. The integral of 1 over y dy equals the integral of k dt. By the way, why did I choose dt and not dx? In these examples, which we will see now, it is often a rate that a change of a quantity through time, like money changing in the bank or population increasing or decreasing. So we would use t rather than x. The integral of 1 over y dy is ln of the absolute value of y. The integral of a constant is simply k, the constant, times the variable, so kt plus a constant c. If we take the exponential on both sides, absolute value of y equals e to the power of kt plus c. Be careful, the plus c is at the exponent. It's not ae to the kt plus c. It's really e to the power of kt plus c. Now that means y can be equal to plus or minus e to the kt plus c if we don't want to have absolute values. This is an explicit expression for y. Using properties of exponents, we know that a to the power of b plus c is a to the power of b times a to the power of c. So let's look what we had here. A to the power of b plus c equals a to the power of b times a to the power of c. Why do I do that? E to the power of c is still a constant. C is a constant, e is a constant, so e power c is a constant. I'm going to give it a new name. I'm going to call it capital C. E to the power of c equals capital C. So this capital C can be brought in front, and we now have y equals plus or minus capital C times e to the power of kt. We have two constants in this equation. We can choose values for both of them. Finally, if y is greater than 0, then we can only focus on the positive values of capital C. Y equals C E K T. It's often like that because, as I said earlier, in these exercises we're going to talk about money in bank, populations in cities, or bacteria. So the quantity y is often going to be a positive number. We don't have negative populations, for instance. If k is greater than 0, then we talk about exponential growth. If k is less than 0, then we talk about exponential decay. So this example, we won't solve it, we just set up the equation. $1,000 are invested in an account that pays 6% interest compounded continuously. Recall what you learned in pre-calc. to write a formula for the amount of money at any time t. What formula did we use in pre-calculus when we were solving these kind of problems? Well, some people just say it's APERT. A equals P times e to the power of RT. P is the principal, A the final amount, R is the rate, and T is time. Why do we show that? Because in fact A equals PERT is precisely Y equals C times e to the power of KT. K is the rate, and we can observe now that capital C is actually the initial amount of money, the principal, the initial population, etc. So this formula really is this formula. In this case, the principal is 1,000 and the interest is 6%, so the rate is 0.06. Experiments have shown that at any given time, the rate at which a radioactive element decays is approximately proportional to the amount of radioactive element present. The half-life of a radioactive element is the time required for half the amount present in a sample to decay. The process is called radioactive decay. Carbon-14 has a half-life of 5,700 years. Find the age of a sample in which 10% of the carbon-14 has decayed. I know there's a few tricks to solve these equations, these problems faster, but I'm just going to go the long way because we tend to forget tricks. But if you just know the general system, then you won't forget it. So here, we don't know in this exercise how much carbon-14 there is. It doesn't matter. We're just going to say there is 1 unit of carbon-14, and we know that it takes 5,700 years for half that amount to decay. So after 5,700 years, we will be left with half a unit, half of what we had originally. Solving this equation for k, we can ignore this 1, of course, so it's ln of 1/2 equals k times 5,700, and therefore k equals ln of 1/2 over 5,700. I'll just use a property of logs here. What did I do? I used this property, ln of b to the power of a equals a times ln of b. And in this particular case, I actually had a equals -1. So b to the power of -1 is 1 over b. And so I can bring the -1 in front. It becomes -1 times ln of b. So that's how, from ln of 1/2, I wrote negative ln of 2. b is 2. Be careful, this is ln of, open parenthesis, b power a, close parenthesis. It's not ln of b and all that power a. It's very different. So now that I found the value of k, I can read the second part of the problem. Find the age of a sample in which 10% of the carbon-14 has decayed. So from my original 1 unit, 1 times e, blah, 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 10% has decayed, so I'm left with 0.9 units of carbon-14. 0.9 equals e to the power of that constant k times t. So I find t equals this exact value, which can be rounded to 3 decimal to 866.417 or 866.418. Obviously it's not going to be that precise, but since we're doing math, we'll keep the 3 decimals here. So the sample is about 866 years old. So there we go. The objectives were to use separation of variable to solve a simple differential equation. This is separation of variables, putting y's with dy, x's with dx, and then integrating to solve. Use exponential functions to model growth and decay. It's really APERT, but we will write y equals c times ekt in AP Calculus.